swap and delta complexes the two things that just represented
yeah, because you can't put that could be added there by
I don't
I should be taking it as a no, but it's your business period. It's not a very
Those are all the notes.
That's not important. So it is, but it's
Okay, so Professor Darden and I actually improved the slides a little bit after we posted them, but it's not too significant. So I'll show you the primary places where it's different. So we've got an example here of a problem, and which I can't remember this semester, I didn't check closely enough. Was this one of your written problems, the code writing problems for the lab? Not yet? Okay, we've done it in the past. We might have changed it this semester. I forgot to check. So for example, suppose I ask you to find the element in an array, unsorted array. I tell you there's an element that occurs more than half the time. Find it for me. Not too hard to do until I start adding constraints like linear time and O of 1 memory. So linear time, if I was allowed more time, I could sort this, right? I could pull out an n log n sort it, and then I could just say, hey, where's the biggest group of consecutive numbers that are the same? That's the one. But we don't have that. If I was allowed to use more memory, we could pull out some cooler data structures that would allow me to do different things, and we're not allowed that. So this one is a little bit harder to do. The thing about it is, so if you want to think about how to do this yourself, remember linear time means O of n. But going through it once or twice or 3 times is fine as long as the number of times that you go through the array doesn't depend on the length of the array. So whether there's 10 elements or 1,000, if I go through it 2 times, that's still O of n because it's 2 times O of n. So that's the key to this one, is going through it twice. Now this one is actually a really well-known problem, and it's solved by what's called Moore's voting algorithm. Now, suppose that instead of more than half of the time, it was instead more than 1/3 of the time, or more than 1/4 of the time, or more than n over k of the time, where k is some value that I pick, like more than 1/7 of the time. Well, to do that one, to do the more than n over k of the time, we have to relax the constraints just a little bit. If it's n over k, I have to allow O of k memory, but I can still do it in linear time. This one is solved by what's called Misra-Grease, which is basically just a modification to Moore's voting algorithm, and it uses a hash table. as the data structure, and we have to basically limit the size of the hash table. So this is a good problem to look at. Smaller problem, 4 lines of code. So the question is, what happens here? I've got an array of doubles. How big is this array of doubles? I didn't say, but how big is this array of doubles? It's of size 3, right? I didn't say, but the initialization list says there's 3 items, so I could have inserted a 3 in there. So I know array A has 3 items, 1.1, 2.2, 3.3. Line 4 definitely works. What about line 5? Is line 5 going to end up being a compiler error? Is it going to be a runtime error? Or is it going to work? And by working, I mean no seg fault, no, Valgrind wouldn't complain about it. It runs and gives output. All right, think about this for a minute. Talk to your neighbors, and I'll give you a hint in a minute. Okay, so before I wrote the hint up there, how many people think this is not going to compile? Okay, how many people think this is going to cause some problem at runtime, like a seg fault or something like that? All right, how many people think it's going to run just fine? Okay, what are you basing that on? The fact that I wouldn't give you a question like this if it didn't compile? Because the thing was, Professor Markov asked me this last semester over the phone, and the first thing I thought of was, he wouldn't be asking me this if it wasn't surprising result. So then, partly based on that, I knew what the right answer has to be. This is going to work just fine. And in fact, lines 4 and 5 are going to give exactly the same output. And the reason is pointer arithmetic. What happens is the compiler converts these 2 expressions to dereference A plus I or dereference I plus A, address plus integer or integer plus address, and plus on pointers and integers is commutative. Order doesn't matter. So it actually gives exactly the same output. So just when you thought you knew how arrays and subscripts work, it's actually more confusing than that. Now the good news is, vectors work exactly like you would expect. If you have a vector of like strings, you can only take a vector of strings and subscript by an integer. But here, whether it's doubles, I could even have a vector of string objects. It would still, well, a vector of string objects would not work because it would give different output. It gets interpreted differently. So with objects and vectors and containers and stuff, this doesn't work. But with just straight arrays, it does. Yes?
So just like vectors, they have like overloading.
Because, yep. So because things like vectors and string objects overload operator square brackets, we get their version of square brackets, not pointer arithmetic version. Exactly. Okay, so one thing about these slides is we've still had a little bit. I eliminated some of it. But there's still a bit in here about how C arrays work, including multidimensional arrays, how pointers work and multidimensional pointers, and how C strings work, and actually I think I've deleted most of the library functions about them. The issue of these is that For projects, we would say, hey, let's use things like vector for our project. I don't want to go and write dynamic memory myself. Let's take advantage of vector or array, etc. So we generally, in 281, will generally avoid pointers when we can. We'll use them when we have to, but we'll avoid them when we can avoid them. Instead, we'll use things like the STL containers, like vector, etc., DAC, and we'll use things like integer indices or iterators, and we'll use C++ string objects. But part of the reason to know these things about basic pointer and use of dynamic memory is, besides interviews, also legacy code. Is when you graduate or get an internship, either get a permanent job, summer job, it's unlikely that your employer is going to say, whew, now that we got a programmer, we can start coding. No, generally you're going to head there and there's going to be like 1 million lines of code to greet you, and it might have gotten started 20 years ago by someone who learned programming 30 years ago, and they wrote everything in C strings and dynamic memory, etc. Like when I first created the word morphing project, I said, okay, I've got to sit down and write a solution, and I want to be efficient with memory, so I'll make a vector of dictionary objects, but each dictionary object will have a pointer to dynamic memory of exactly the right number of characters. And I went, no students are going to do that. Let's just go with the vector of stuff including strings. And so sometimes my reaction like that, I have to say, no, let's do something more reasonable like the students would do it. But it's still good to know some of these things. So a little bit about pointers. Arrays are pointers, pointers are arrays. So when I create character array AR, again, the size is not stated, but the initialization list in curly braces lets the compiler determine the size. So the size of this array is 4, and we show it over in memory there. I changed array element sub 0 to be back to an E. So I can store a character into the array. I can get a copy of a character in the array back out of the array. I can make a new pointer, PTR, that points to the same place that AR refers to. AR refers to the array. PTR is a pointer that refers to the first element of the array. But pointer PTR and array AR are almost the same. There's one thing that you can do with PTR that you can't do with AR. What can you do with PTR that you can't do with AR? It's actually in this slide. Yeah. Yeah, we can do line 10. We can say, hey, PTR, you don't point there anymore. You point to this one. But AR is required to always refer to the array that it started as, because if we didn't, then we might leak memory. If AR was allowed to refer to something else in memory, then who would refer to those 4 bytes of letters? We'd lose it. So pointers and arrays are basically the same, except arrays cannot change what they refer to, pointers can. So when I changed pointer PTR here, I can say ampersand array sub 1, the address of array sub 1. I can add parentheses if I want to make it a little bit more clear that the subscripting happens first and the address of happens second. I can also do it with pointer arithmetic. I can say pointer equals array plus 1. I can do pointer plus plus. I can do plus plus PTR, etc. So these array objects allow us this random access. I can skip to any element I want in O of 1 time. It takes no longer to get to element 3 than it did to get to element 0. The index numbering always starts at 0. There's no bounds checking of these arrays. And the size of the array, if I need to keep track of it, I'll have to store it somewhere else, like in another variable. Why is there no bounds checking in C++? Why don't we get things that, hey, at runtime it says you've got an invalid array subscript at line 57? I'll give you a hint about whys in C++. often, not always, but often the right direction to think about the answer is efficiency. Not always, but it's a good place to start thinking of first. It's not a sufficient answer, so yeah.
Because then the array doesn't have to keep track of the size, it only keeps track of the
Right, so first of all, the array doesn't have to keep track of its size. Second of all, I don't have to follow every array access with some more hidden code that checks if that index was valid or not. So it saves a little bit of memory and it saves time. Every square brackets operation is faster. And it's done that way because C++ is built on top of C. The C language was designed why? What was its original reason for being created? The C language was created to write operating systems. Before the C language, every operating system was written in assembly language. And that's a lot of work. Someone changes the architecture a little bit. Oh, let's just rewrite those 700,000 assembly language instructions. So some people decided at Bell Labs, hey, we should have a better way of doing this. Let's write a language that will be so close to assembly language, so fast, so efficient, that we can write most of the operating system in C, and then we'll write just a little bit of it in assembly language for each particular architecture, but like 95% of the operating system will be completely generic and will work anywhere. So that was the goal of C, was to be fast, fast, fast. As fast as writing assembly language yourself with a really good compiler. But because of that, there has to be things that it does not do that are your responsibility. Now, when I create a one-dimensional array, or I create a two-dimensional array, we think of them, so I think of it this way. How it's actually laid out in memory, they both look like that. So in memory, a one-dimensional array or a two-dimensional array looks exactly the same. When you say, hey, I think I have a two-dimensional array and I want to access some row and column, like I want to refer to like A2D sub 1 sub 2, well, this is 1 is the row number, 2 is the column number. It takes the row number, multiplies by the number of columns, that's 3. So that's 1 times 3 plus 2 is it says you should go to index 5 of the one-dimensional array. Well, index 5, 0, 1, 2, 3, 4, 5, that's this element over here. So what I think of as this element, really in memory, refers to this element. If I want to, I can create in memory, I can create a one-dimensional array, and I can treat it as if it was a two-dimensional array. I take the index that I want to get to, and I can change that index into a row and column number. So I can, the other way around. So if I create a two-dimensional array, I can treat it as a one-dimensional array. Take the one-dimensional index, do div and mod, gives me the row and column number, and I can treat a two-dimensional array as if I accessed it with one index. That's a little bit rare. Treating a two-dimensional as one is kind of rare, but creating a one-dimensional and treating it as two-dimensional is more common. Now we could do a fixed size array. So I could do a two-dimensional array. Again, here, rather than just doing 3, 3, here I actually created some named constants. So I've got my named constants and I create those. I create the fixed size array of size 3 rows and 3 columns. And then I go through every row, every column, put a value in there. So this fills it up with these values over at the right. Now I could, if I wanted to, I could declare a fixed size array 3 by 3. I can give it an initializer list with the curly braces. I can separate each row inside of its own set of curly braces, make it really readable. I could fill it up with, like, instead of 0, 1, 2, I could fill it up with 1, 2, 3 or whatever I wanted. So either way, I end up with a 3-dimensional array. The nice thing about doing the fixed size arrays is there's no pointer, so it's a little bit safer. I don't have to clean up after myself and delete memory when I'm done. The size of the 2D array here, the fixed size of 2D array, actually has to be known at compile time. The size of this array over here must be known at compile time, and that's what the named constants do. Now in G++, we're actually allowed to use variables. In G++, I could get rid of the word const. I could get rid of the initialization to equals 3 equals 3. I could read it in from the keyboard. I could read the size in, and G++ will let you do that, but in general, you can't. Visual Studio won't accept it. The LLVM compiler for Xcode won't accept a variable size array, but G++ does. The other thing is this will use a little bit less memory than our pointer version. We'll look at that in just a minute. So if I wanted to create this with pointers, now here I could have done a little bit more room. Let's change this code a little bit. We could get rid of the word const there. We could get rid of the equals 3s, and we could add a line of code under this to just say cin greater than rows greater than columns, and so semicolon. And this code will work because we're doing it with dynamic memory. The size doesn't need to be known at compile time. So we can read the size in. So assuming that someone typed in rows and columns of size 3 each, then this picture makes sense. So we create then, we said I'm going to create at line 3 array, ARR, is an int pointer. Okay, if I created just an int pointer of size 3, what would be an int pointer of size 3? If I say something like b equals new int sub 3, right? Then b is a pointer, it points to a block of memory of size 3 with room for 3 integers. So that's if I did a new int of 3. But over here I'm doing a new int pointer. So what array ARR here is, it's an array of size 3. Oh, wait a minute. ARR is a pointer. ARR is a pointer that points to this block of memory. This block of memory has room for 3 pointers to integers. So ARR is a pointer which points to an array of size 3, each element of which can point to 3 integers. We haven't finished the rest of it yet. So that's after line 3, we've got this array object. Then line 6 and 7 say, hey, let's go through every row of this thing and initialize each of those elements to point to a block of size 3 columns. So the green here, the green numbers, I think that's green, the green numbers there are the subscripts. So this is row 0, row 1, row 2. The green numbers in here are the columns, column 0, column 1, column 2. So the green numbers are the subscripts. And then after line 7, we've got this whole 2-dimensional pointer structure built. Then lines 9 through 14 fill it in with values. They put the 0, 1, 2, 3, 4, 5, 6, 7, 8 in there. For every row, for every column, set array sub r sub c equal to a value. And then we could add more code. Below line 15, like between 15 and 16, we could add more code. We could go and print out this array. We could go and change it, do whatever we wanted to this 2-dimensional array. But when we're done with it, we need to go and delete the data. We don't want leaked memory. We want to clean up after ourselves. The important thing is we have to, when we clean up after ourselves, we have to destroy it in the opposite order that we built it. We can't just delete ARR first. If I delete array ARR first, I won't have the pointers to all of these rows that I allocate. So we go through and we delete the rows first, then we delete the original array. So we build it up, we build array first, then we build the rows. When we destroy it, we destroy the rows in any order. Doesn't matter whether we destroy them row 0, 1, 2, or 2, 1, 0. We destroy all the rows before we delete ARR. Let's see, what was I gonna say? Oh, the other thing is about the memory. We mentioned on the last slide here that this version uses less memory than the next one. Well, this one basically is laid out in memory like this right here. This needs room for 9 integers. How much memory does our version over here require? It's still got 9 integers, and it's got 3 int pointers. So the pointer version takes a little bit more memory because we've got to have the pointer to each row. Now either one of them will have a pointer to the whole thing. The array version, I'll have an array variable which points to the whole thing. Here I have ARR which points to the whole thing. But this one has 3 integer pointers, or whatever the number of rows are, will have that many extra pointers. Yeah?
How does the array deletion operators know how big the dynamic allocator is?
We're going to get to that in a few minutes. So he wanted to know how it knows when I say delete square brackets, how it knows how big each one is. We'll get to that in a little bit. Okay, so there's my 2-dimensional pointer version. So we had the 2-dimensional fixed size array, the 2-dimensional pointer version. Now, when we use these, there's pros and cons to each one. So the nice thing about the fixed size arrays is that they're actually allocated on the stack, not on the heap. What's nice about that is that when the function ends, like if I declare a 2-dimensional array in function A, when function A is done, the array gets deleted for me. There's no need to clean it up. It was on the stack. Everything on the stack goes away when the function ends. The other nice thing is that the fixed size array, ARR sub I sub j, accesses memory once, not twice. So look over here. When I say over here, I want to access, this is getting crowded, whoops. When I say I want to access like array sub 1 sub 2, what happens is it does a little bit of math, but then once it has this index, it goes over and looks at that element of the array. And so it involves a little bit of math, but then one time it needs to look into memory. Over here, with the pointer version, in this one, when I say I want to access array sub 1 sub 2, it actually happens in 2 pieces. It accesses array sub 1, and it says, oh, array sub 1 means this row, so it has to look at this element, then it knows you want to look at that row, then it takes this row and looks at subscript 2 within this row and goes to the last column. So I have to look at 2 different places in memory, which is a little bit slower. Okay, so the fixed size array only uses 1 memory operation. The downside is large fixed size arrays, because they're allocated on the stack. Remember, the stack is a lot smaller than the heap. The stack might have room for like 2,000 function calls deep, but the heap might have room for 4 gigabytes. So the stack is a lot smaller, so allocating big arrays on the stack might not work. Your program might not even be able to be started, or you might start your program, allocate this huge array in main, go to call function A, and there's no stack space left to even call one function. The other downside is the size is fixed at compile time. Fixed size arrays, we can't change them. They must be known at compile time. The other painful part about multi-dimensional fixed size arrays is they're a pain to pass to functions. When you pass a 3-dimensional array to a function, the function actually has to know at least 2 of the 3 sizes. So if you've got an array of size 10 by 20 by 30, the receiving function must know 2 of those 3 sizes must be known. The other thing is with fixed size arrays is you don't want to use fixed size buffers for variable length input. This leads to a lot of, we had an estimate, so one of the security professors said, I think about 70% of the security flaws we see involve these buffer overruns. Buffer overruns have been around for 30 years now. There was the Tappan worm years ago. This guy named Tappan figured out, hey, there's a program on Unix, which I'll admit, Unix programs have weird names. So there's a program on Unix called Finger. The Finger program lets you find out who someone is. Basically, you say finger space unique name, and it tells you more about the person, like their real name, and each person is allowed. Like if you create a .plan file or a .project, it'll show up in the finger info. But 30 years ago, someone figured out, hey, when you type something like finger, like Smith at umich.edu, the finger daemon, the program running on that other server waiting to receive the finger request, is assuming this thing is going to be 8 bytes long. But it doesn't have to be 8 bytes long. I could finger 1,000 characters at some other machine. What happens to those other 992 characters? They overwrite the finger daemon. So he wrote like 992 bytes of data that was actually instructions to the other machine. What did it do? It modified the other finger daemon to do the same thing every time anyone ran a finger on that machine. He didn't even need to know all the addresses that existed. He just needed to let users type in addresses of people at other universities, and bam, the internet, the tap and worm spread across what wasn't even the internet back then. It was like a combination of DARPANet and BitNet, spread to every PDP 1170 in like 3 days, just through this finger daemon. Now, if you look at Kane machines, still 30 years later, the finger daemon is disabled. It doesn't work. They got rid of it. So you'd think, oh, well, hey, that 30 years ago problem, we've solved that right now. That doesn't happen anymore. When did a big buffer overrun function problem come into the news? About 2 years ago. Heartbleed, yeah. Heartbleed, the heartbleed bug was based on what's called the heartbeat. When you open up a secure connection and you get like your little shield icon up in the corner that says you've got a secure connection, encrypted connections take resources. So servers are allowed to say, I'm not going to keep this connection open if you're not still there. And so sometimes your client is required to send a heartbeat to the server to say, I'm still here, keep my connection active. But I also want to know, is the server actually keeping my connection active or not? So what the heartbeat did was, instead of just saying, I'm still here, I say, I'm still here. Here's 64 kilobytes. Here's the letter A. The server says, oh, I will copy your 64 kilobytes, or actually, sorry, I will allocate a buffer of size 64K. I will copy your letter A into it and give it back to you. What's in the buffer now besides the letter A? Whatever was in memory. Usernames, passwords, credit cards, social security numbers, private encryption keys to the server itself, basically anything. So the heartbeat bug had the potential to expose any piece of data on the server to anyone who did a heartbeat to that server. So Professor Haldeman has a program which existed before that. He already had a program that could basically scan every internet-connected computer in an hour. So he and his grad student took like 2 hours to write a heartbleed test, ran it like 3 hours from the announcement. He knew every computer in the world that was subject to attack by heartbleed, and started writing another program to send out emails to system admins saying, your server's susceptible. Okay, where were we? So if we're using dynamic memory, so nice thing about dynamic memory, these double pointers or single pointers or triple pointers or whatever, all dynamic memory occurs on the heap, so we're not so limited in size. Neat thing, we can do things like triangular arrays. I can say, hey, every row isn't the same size. I've got like row 1, row 2, row 3, row 4 are all increasing sizes. I can swap rows very quickly. In the pointer version, I can say, hey, just swap row 0 with row n-1. Boom, O of 1 operation to swap 2 rows. In the non-pointer version, I have to swap every value within those rows. We can change the size at runtime. We can read in from the user, from the keyboard, from a file, how big the data is going to be and make our memory the right size. The downside to this is that all this versatility comes at a cost. We've got to do our deletes ourselves. We'll leak memory if we don't. We can cause crashes. Any invalid access can cause crashes. Usually dynamic memory can lead to a few more problems than fixed size arrays. Other downside, array square brackets is a little bit slower than with built-in arrays because of those 2 memory accesses. The STL, though, offers something better than dynamic memory. We've got things like vector. So instead of creating a 2-dimensional array, you create basically a 2-dimensional vector. But 2-dimensional vectors don't exist, so what do we create? We can create a vector of integers. So I can create a 2-dimensional vector by creating a vector of integers. And we'll show you, I can't remember whether it's later in this slides or next slides, we'll show you how to create a 2D vector and pre-size it to be like 10 by 20 up front. We can create the size when we create the 2D vector. We've got a couple examples here of different off by 1 errors. So things like saying less than or equal to size when we should have said less than. We access an invalid element. Here we are trying to say, hey, because I'm going to set x sub k equal to x sub k plus 1, I want to do -1 there. But again, we need a less than. So if we're going to set this one equal to the subsequent one, we need to stop early. We need less than and size -1. For the last one down here, I'm trying to set an element equal to, instead of the one that follows it, I'm setting an element equal to the one that follows it, but by doing -1 on the front end instead of +1 on the back end. Excuse me. But then for this one will actually leave one of them undone. We start at 1, but then this one actually should be less than or equal to size. So there's lots of different ways you can get off by 1 errors. And some of the like bugs that we do in the project is things like this, like what if I said less than when it should have been less than or equal to? What if I left out an if statement that I should have checked? What if I allowed like 2 letters to change instead of 1 or something like that? When we look at the for loop, so normal for loops like lines 4 and 5 you're used to, there's actually in C++ 11 and beyond, there's something called the range-based for loop, also referred to as the for each loop, also referred to as the enhanced for loop. So the range-based for loop, what it allows us to do is say, I would like to step through every element of a container. So for instance, if we had here, we've got an array, my array. My array has in it 1, 2, 3, 4, 5. The subscripting version says access an element of the array, multiply it by 2, and store it back in. With the enhanced for loop, we're saying step through every integer reference colon my array. So for every integer reference in my array, multiply x, that variable, by 2 and store it back into x. Well, here the reference parameter, the reference x is really important because if we leave off the reference, if I get rid of that reference, what happens is x is equal to 1, well, x changes to 2. X is equal to 2, x changes to 4, and the array never changes. So if I leave off the reference, all I'm doing is changing x over and over again. But if we put the reference back in, what happens is x is not a variable. X refers to the value 1, and x changes to 2. Then when we come back through the loop, x gets recreated. X is now linked to item 2. When we change x, we change that 2 to a 4. Then we come back through the for loop. X is a new reference which is linked to 3. 3 changes to 6, etc. So if I wanted to, say, print the elements, I don't need a reference. So if I want to say instead of x times equals 2, if I want to say just cout less than x, less than a space, then I could get rid of the ampersand and I could print every element of it. What if these weren't integers? What if these were big objects? If these were big objects, then maybe I want to use the reference, or better yet, If these were big objects, I might use a const reference, and I'm gonna output them. So same rules as like in the Canvas files, resources, optimization tips says, hey, if you're gonna pass things to a function, if it's big, if you need to modify it, pass it by reference. If it's big and you're not gonna modify it, pass it by const reference. If it's a simple thing like an integer, pass it by value. So it's sort of an if-else if. Yeah?
Can you explain again what happens when you do the second one without an ampersand?
Okay, so if I get rid of the ampersand and I do the multiplication, so if I get rid of that ampersand and I do the multiplication, what happens is, it's like, think of this as like a function parameter. If I pass something to a function by value, x gets a copy of 1. And when I change x without changing the original. My array has 1 in it, x has a copy of the 1. When we change x, the original doesn't change. But if we had a reference, if we modify the reference, the original 1 changes. So it's just like function parameters. Okay, any other questions on the range-based for loop? So the range-based for loop can basically be used on any container type that you're allowed to look at the contents of the entire container. So you can use the enhanced for loop with an array, with a vector, with a deck, with a linked list. You cannot use the enhanced for loop with a stack because you're only allowed to look at the top of a stack. Now, when we do new and delete, so when we do new, we're getting one object. When we do new square brackets, like if I say new int sub 4, I get a block of 4 integers. And why would we use one new over the other? Well, it depends on what we're doing. Like if I was creating a linked list, I would use the first version. If I was creating like a vector type object, I would use the second version. Hey, I need my vector to have 4 integers in it. So we base our type of new and delete on what we want to do. Or sorry, we base our new on what we want to do. We base our delete must match the new that we're getting rid of. So if I did a new, I do a delete. If I did a new square brackets, I do a delete square brackets. Now, one of the nice things about delete is that we don't have to tell it the size. So when I do a new int of 4, I don't have to say delete square brackets of 4. The runtime system figures out the size for me. So I don't have to say that up front. If we are creating new objects get constructors called, objects get destructors called. But if we have simple types like int or double, they don't have a constructor, they don't get initialized. So if I say new int of 4, I've got a block of 4 integers, but I have no idea what the values are. They do not get initialized to 0. Now, someone asked before, how does the compiler know? When I try to delete something with square brackets, how does it know how big it is? Well, let's go to new. How does new know how big it is? So when I say like int pointer p is equal to new int, and then later on I say delete p, the compiler says, oh, p, what is p? It's an integer pointer. You must be giving back the size of an integer. You must be giving back 4 bytes. Because that's what p points to, is a block of 4 bytes for one integer. However, when I say something like int pointer, let's say p2 is equal to new int sub 4, p2, what it returns to me is a pointer to a block of memory with room for 4 integers. So this is basically 4 bytes times 4. So there's a block of memory of 16 bytes there. But one other thing. It's got to be able to, when I say delete square brackets p2, it's got to be able to figure out how many bytes are there. And it needs to do it quickly. So that's the that comes to a question. Why do we have two different versions of delete? Why not just let there be one version of delete and figure out the size? Well, efficiency. So what actually happens behind the scenes is the new int of 4, what actually happens is it allocates a bigger block of memory. It returns, it gives you a pointer to the 4 bytes of integer, or for the block of 4 integers, but before it, it puts a size, and this is 4 times 4, there's 16 bytes here. The size is actually going to be 8 bytes, so it's actually gonna have over here the value 24. 24 is how many bytes this whole thing is. 16 bytes of your data plus 8 bytes of size data. So when you say delete P2, or sorry, when you say delete square brackets P2, so when I say delete square brackets P2, what happens is you give it P2, which points here, it looks backwards and figures out the size and gives 24 bytes back to the system. So that's how it happens behind the scenes. And this is why there has to be 2 versions of delete when there's 2 versions of new. If we had 1 version of delete, then every single integer would have to have a size before it. For a 4-byte integer, I'd have a 4-byte integer and an 8-byte size. Here, whether I have 4 integers or 1,000 integers, there's an extra 8 bytes that goes with it for the size. Okay, so when we want to put stuff inside of another variable, like a container, we usually want to have multiple items, right? I want like a vector that I can put lots of things in. And the things that I put in it could be integers, doubles, strings. We could even make a templated container that I can put anything into. We're gonna have some sort of protection and control over the items. And what I mean by that is, like, say, if we were making a stack, we would only let people look at the top of the stack. They can add lots of things to it, but they can only look at the top. They can only pop from the top. We might allow the ability to edit or create or copy multiple items at once. Like I might say, hey, you can only look at the top of the stack, but you're allowed to make a copy of the entire stack. But even in the copy, you can still only look at the top of it. We can create more complex data structures by putting containers inside of other containers. In fact, most of you on Project 1 probably already have something like this. You probably have something like a vector of some, I'm guessing, struct. You've probably got a vector of structs. What does your struct have in it? It's got a string and some other things. What does the string have inside of it? Oh, it's got a size and a pointer to dynamic memory. So just Project 1, you've actually got like a 4 layers deep. You've got a vector of objects which contain strings, which have pointers to dynamic memory. So making these containers of containers allows us to make complex data structures from other things we already have, and then we can build that data structure of containers in a way that is useful for us, that allows us to do the operations we want to perform in searching through the data that we have. If we look at a database, like a database program, like a SQL database, it's really just a set of fancy containers that happen to reside on hard drive. The autograder is backed by a database. Every time you submit, there's an entry created for your submission, like who submitted, what time, what was the file, how many points did they earn, et cetera. Then every test case that you run generates another group of data, like what test case, so like what user, what project, what timestamp, what test case, what did it do, how many points did they get, et cetera. So just one submission actually creates dozens of database entries on the server. So examples of containers that we have so far, well, we've already talked about the project has vector and string and deck, right? If you're using a deck instead of a stack or a queue. We've got the array we mentioned today is not as useful as vector because it's fixed size. The STL has a linked list, stacks and queues, maps, unordered maps, lots of things in the STL we're going to be looking at as the semester goes by. So looking today basically at array-based containers as an example. Later on, we're going to look at ordered and sorted ranges, heaps, hash tables, graphs, etc. So any container, whatever I'm creating, I probably want to have, a constructor. I've got to be able to create a container. I should be able to destroy a container, add something to it, remove something from it, access an element, whether I'm allowed to access the top of the stack or an element at index 57. I'll have some way to get an element in that container once it's in. I might want to know the size. Hey, container, how big are you? Maybe I might want to make a copy of the container. I might want to assign, so I might want to add an element and then change the value of that element with an assignment type operation. So what other things might we want to do? Hey, you're creating a container, it's going to do what you want. What do you want your container to do? What other things would you like it to be able to do? Yeah. Okay, so we could have some sort of order changing, like a reverse operation. Hey, that would have been really useful for project 1. We could have a reverse operation. We could have maybe a sort operation, something like that on our container. What else might we want to do? Maybe a comparator. So we might have to say, hey, I've got 2 containers of integers. Which one is bigger, whatever my definition of bigger or smaller is. So I might have some comparison. Or are these 2 containers equal? We might want to say, hey, I'd like an output operator. Because I can create a vector of ints, but I can't say cout less than v. There's no output operator for vectors. So if I'm creating my own container type, maybe I'm going to create my own output operator. So it's easier to display what's in the darn thing when I'm done with it. So we can do lots of different things. We need to decide, how are we going to store the data internally? Am I only going to allow sequential access like a linked list, or am I going to allow random access to my container, like you can skip directly to index k? So linked lists and disks are basically our examples of sequential containers. Random access is used by array, vector. DEC actually has O of 1 square brackets operation. We don't need it for project 1, but it's there. The main memory in our computer. And once we have random access, we can still do sequential access to our random container. I can still go to array element 0, then 1, then 2, then 3, then 4, or I can access it sequentially, I can access it randomly. But once I'm locked into a sequential container, it's hard to go directly to index k. I generally have to read all the elements 0 through k to get to element k. Now, if I'm going to store items in an array, hey, we might have to do some copying of an array later on. Maybe we should know how to copy an array. Well, if I've got some source array and a destination array, I can use a for loop. I just use a for loop, copy elements from one array to another. Or I can pull out the pointer version. I can say, hey, let's get a source pointer and a destination pointer, and then I can set them equal that way. So for example, if I had source array has right now 3, 5, 6, 1, and my destination array right now has nothing in it. So then it says, the pointer version says, give me a start pointer that points to the start of that one. So I've got SPTR. So SPTR points there. Destination pointer points to there, where there's nothing there yet. So while my source pointer is not equal to source array plus the size, dereference the destination, set it equal to dereference of the source. All right, so that says copy the 3. So this statement says copy the 3 from the source to the destination, and then after you've finished the copying, increment both pointers, because it's a post-increment operation. The increment happens last. So then basically we move the pointers. So they don't point there anymore. Now they point to 5 and the empty element there. Go back through the loop. Overwrite this empty value with a 5, move the pointers to point to 6 and this one, copy the 6, move the pointers again, so now they point to here and here, copy the 1, and then after I copy the 1, we end up incrementing both pointers. So after we increment those pointers again, I just erase here a little bit. So after we increment those pointers again, where do they point to? They point to basically just off the end. Well, the while loop says, while the source pointer is not equal to source array plus size. Well, source array points to the first element. Where is source array plus size? It's 1 past the end. Source array plus size points to just past the end. So when I say proceed as long as it's not equal, now is the time to stop. So it says as long as they're not equal, keep going. When they are equal, we have to stop. Now, could we, in this case of these arrays, could I change that not equal to and change it to less than? Would that still work? Yeah, that'd be fine, because these are, remember we said arrays are laid out in memory sequentially, so we go from one address to another. This would work just fine. But there's a reason to prefer to use the not equal to. The not equal to works in more circumstances, and part of it is related to the why. Why use the pointer version when we could do without it? Well, the pointer version is actually going to be a little bit faster, and it's more versatile. If we look at like vectors, we can use subscripts on a vector, but we can also use iterators on a vector. Iterators are like pointers. We can do iterators to a linked list. Iterators into a vector, less than would work. Iterators into a linked list, less than is meaningless, because in a vector, memory addresses are actually sequential. But in a linked list, node 1 could be here, node 2 is over there, node 3 is back here, node 5 is up there, node 57 is right next to node 0. Less than is meaningless to a linked list. So not equals is safe for all different types of pointers and iterators. Not equals is always safe. Sometimes less than works, sometimes it doesn't. So that's why we prefer the not equals. Now, what am I actually going to put in my container? Let's say I've got character data. What am I going to put in my container? Am I going to make a vector of characters, a vector of char pointers, a vector of char references? What am I going to put inside? Well, if I store characters, then the container gets to control all the access to those characters. The downside to this is if I don't put characters, if I put like student objects go in my vector, student objects take a while to copy into the vector and copy out of the vector. But it turns out this is actually the most common thing to do, is create a vector of student objects, create a vector of dictionary entries. Whatever we're doing, it's most common to put the data type in the container. All right, what about pointers? What if I said, hey, I've got some character data and I want to put pointers to it into my vector? Well, I can do that, but then the question comes up, who owns it? In the character data, the vector owns what's inside of it. But here, now I've got a vector, and the vector stores pointers to somewhere else. The question is, who's responsible for that other data? Is the vector supposed to be responsible for it? Because from the vector standpoint, it is not. The vector is only responsible for the thing that it does a new on. If that new happens to be a container full of pointers to other places, you're responsible for the things that you put in it. Vector's only responsible for what it has. Downside to this is it's somewhat unsafe. If I've got character pointers stored in me, and what if I've got, hey, I'm a vector, I have pointers to some other data which someone deletes. Now the vector's broken because the vector's full of pointers to things that don't exist anymore. Now we sometimes use this. If we do have like big string data, we might create a vector of char pointers. It's also useful for shared data. Like if I've got, say I've got a vector of student objects and I want to have some other data structure that can manipulate it, I might say, hey, let's not make copies of all those students. Let's keep the students where they are and make some data structure that points to those students. And that's safe as long as all the students still exist. If a student stops existing, I've got to get rid of it in my container too. So shared data is a place where we will do that. Okay, what about if I want to put references? Like the data's over there and I want to have a reference to that data. Well, there's a problem. First of all, there's no ownership. You can't delete references. You can't change references. So once I have a reference to that character, if you try to change the reference, you actually change the thing it refers to. And this is not useful. In fact, if you try to create a vector of char references or a vector of int references, you'll get some really cryptic compiler error message that may or may not be readable, but basically you can't do it. It just doesn't work behind the scenes. The things that vectors need to do to keep the data does not work with a vector full of references. Okay, let's assume that I'm going to keep the common thing. I'm going to have a vector of characters. Then if someone asks me, hey, I want to look at element 5 of you, I have to return something. What should I return? Well, how about just a value? You want to look at index 2? Fine. Here's the character at index 2. You can have a copy of it. Downside to doing that copy is if these aren't characters, if these are student objects, and I have to say, here's a copy of the student object at index 2, that takes time to do all that copying. All right, I could instead give you a pointer. Like I've got my own array, like I'm a vector. I have, internally I've got dynamic memory to store 100 student objects, and I will give you a pointer to one of them in the middle. Well, now you can do anything you want because you've got a pointer. You can go to a different student. You can go back by 1 and forward by 1, change different students. You can go back by index 3 and get 3 indices. Say, hey, let's go back from index 1, let's go backwards 3 and change that student that doesn't exist. You can get seg faults, you can modify other students, all kinds of bad things happen if I give you a pointer to my internal data. Not a good idea. I could give you a reference to my data. So I could say, here, yeah, I've got internal data, you can look at it, and I might give you a reference, you can look at it and you can change it, or I might give you a const reference. You can look at it, but you can't change it. This is actually a very, very common choice, and this is what, like vector, when you say vector v square brackets 1, when you use square brackets on a vector, that's what it does, is it gives you, actually it has both, a reference and a const reference. So we'll look at, in a little bit, how to create an array object, how to create square brackets operator, and we're actually gonna write both versions of the return a reference to something internally. The nice thing about the reference is it has none of the downsides of either of them. It doesn't have the speed cost of copying, and it doesn't have the safety problems of a pointer, because once you have a reference, you can only look at that one. If I let you change it, yeah, you can change it, but you can't change a different one. Now, when we have an object, a container object, we might have, say, pointers to dynamic memory. It's dangerous if 2 different objects point to the same dynamic memory. What happens to A if I modify object B here? Well, object A gets changed. You're saying, hey, I'm not changing object A, but the data keeps going black on me here. Well, that's because you let them actually have pointers to the same object instead of having separate copies. What happens now when I delete array object A? Let's assume I actually did something right and I've got a destructor. So when object A gets deleted, what happens? The array gets deleted also. So now when B goes to access its data, it's accessing things that no one is supposed to access anymore. What happens later on when array B gets deleted? I go back, yeah, it's called a double delete. I go back here and I say, hey, delete this memory. The runtime system immediately stops you and says, nope, you're deleting something that's already been deleted, error. And it just stops the program. So all kinds of problems happen when we have these shallow copies, when we have 2 different objects pointing to the same block of dynamic memory. So we should have duplicate objects created. We don't want to have multiple pointers to the same objects. If we do the default copy constructor, then what we get is what we don't want. We get the issues we just talked about. We get two things that point to the same object, all kinds of problems happen. So there's two ideas of ways to solve this. One way is every object is owned by somebody, and that somebody is responsible for it. If you do the new, you're responsible for the delete. And that's generally what we do in C++. In Java, Java has no ownership. You want to do a new, that's fine. When nobody refers to something, someone else is responsible for freeing it. So anybody can do a new, but then something, it's called the garbage collector, has to look around and see that, hey, I used to have a pointer P, oh, actually Java doesn't have pointers, it has references. I used to have a reference to object A, and now I don't anymore. The garbage collection notices that, says, hey, no one actually has a reference to A anymore, I can free up A. Well, what if A has a reference to B? Well, when A gets cleaned up, then B can be cleaned up. But what if B refers back to A? Now when P disappears, you've got to be tricky enough to notice that A and B actually have this circle of stuff that has all references to things that nobody refers to, and you've got to notice that. So that's the Java solution, is have no ownership, have a garbage collector that runs, and basically Java has no destructors. There is no way to tell. You can't even count on when an object will be destroyed. Your program might end and your objects might still exist for a while. We can actually also do this in C++. C++ has libraries of smart pointers called unique pointer, shared pointer, etc. Unfortunately, you're not allowed to use them. I asked about this though. I had a IA who said, no, people in 281, they're great with pointers. Just let them use smart pointers. I said, let's ask Professor Kiris. He teaches 381. I said, should I teach them smart pointers? He says, oh God, no. He said, they come into 381, I have to teach them pointers all over again because lots of students still can't do everything quite right. So he said, if they want to learn smart pointers, send them to 381, but don't do it in 281. So I took his advice. All right, so when we have memory ownership, objects could be owned by another container. So that's fine, but we've got to make sure that the access is correct. So for privacy and safety, if I own something, I control the access to it. I don't want other people looking at it except in ways that I let them to, that I allow them to. So we don't want to allow double deletes, etc. So the destructor should be deleting each object and cleaning up after things and not having memory leaks. One thing you can do to help in programming is when you do delete things, immediately set the pointer to a null pointer. Don't just delete it. Do the delete and set it equal to a null pointer. Even if later on, like I say, delete pointer, pointer equals null pointer, delete pointer, perfectly safe. Because deleting something that is equal to a null pointer does absolutely nothing. It's safe to do. So what's wrong with memory leaks? You say, well, hey, we've got modern operating systems now that clean up after you. This isn't Windows 95. In Windows 95, you could run a game twice, and the second time the game would say there's not enough memory, because the first time you ran it, it didn't delete anything. So now modern operating systems, multi-user, multi-application operating systems clean up after every application. As it ends, memory is freed. But if we don't do this, we might write a little toy program to prove that something cool can be done and find out, hey, let's take this cool little program and roll it into our primary system. Now, if that cool little program didn't clean up after itself, our system doesn't clean up after itself. Or what if you're doing, hey, I work for a company, what do? I make smart refrigerators. It texts people when they're out of milk and all kinds of cool stuff, but there is no operating system in the refrigerator. Your program doesn't stop every hour and get restarted. Your program doesn't stop until the refrigerator gets unplugged. You can't afford to leak memory every time you send a text. So you've got to learn to clean up after yourself. The autograder does two things. It severely limits memory. We've got, I think, the 32 gig machine, no process is allowed more than 4 gigs. So 6 students at a time, that's 24 gigs. Even 6 students can't use more than like 24 out of the 32 gigs. So you can't use more than 3/4 of the memory. Also, when it's done, the autograder runs Valgrind to check for memory leaks. So you should too. Valgrind tells you about more than memory leaks. It does uninitialized variables, etc. So here's our starting point. We're saying, hey, let's create our own array class. We're going to create this object. You're allowed to say, I'm going to have an array object of double data. Well, double data, that's fine. We could change this to integer data, character pointer to data. We could get this working with double, and then we could turn it into a whole templated system and just put any type in it. So we're going to do this whole example with doubles, but we could later on change it to a whole templated class. So inside, I've got a pointer to my data. I've got an unsigned integer length. I've got a constructor. We'll come back to the constructor in a minute. I've got a size function, which just returns the length. And then we're going to have other member functions in the next couple slides. So the constructor says, you have to give me a length, but if you forget, I'll just assume you wanted an array of length 0. It does the initializer syntax here. It says initialize the length member variable off of the len parameter. And then it says set data equal to length question mark new double of length colon null pointer. So who is not used to seeing this question mark colon syntax? Okay, lots of you. All right, this thing is called the ternary operator. So remember, unary operators like minus minus have 1 parameter. Binary operators like multiplication have 2 operands. Ternary operator must have 3 operands. So what the ternary operator says is expression 1, question mark, expression 2, colon, expression 3. What it means is the result of this entire ternary expression depends on expression 1. So we check, is expression 1 true or false? If it's true, the result of the entire thing is expression 2. But if expression 1 is false, the result of the whole thing is equal to expression 3. Now, there's nothing we can, I shouldn't say nothing. There's places where ternary is critical, but for most places, we could replace a ternary operator with an if-else. So for example, what this is saying is, if length is true. Wait a minute, length is an integer. What does it mean when length is true? Length is non-zero. So if length is non-zero, set data equal to a block of memory of that length. Otherwise, else, set data equal to null pointer. So we could replace this line with 4 lines of code. If length is greater than 0, set data equal to new length of double, else set length equal to null pointer. So I can replace line 7 with 4 lines of code, but ternary operator makes it shorter. The danger of the ternary operator is overuse. So here, yes, it's cryptic at first, but once you start seeing it and understanding it, it's not too bad to see 1 ternary operator. What you don't want to do is say, hey, let's replace expression 1, 2, and 3. Let's replace all of those with more ternaries. And what goes inside of those? More ternaries. What goes inside of those? Function calls to more ternaries and loops and everything else. If you want to see code like that, look at the obfuscated programming contest. Obfuscate means to hide. So there's a programming contest every year. They say, hey, you've got X number of characters. Like, it used to be like 512. So maybe this year it'll be like 600. 600 characters, write a program that is unreadable by humans and does something, and you get bonus points if it does something cool. So you look at this program, it's like for loop. What's the start and end and update conditions? All ternary operators. What's inside of the for loop? More ternary operators. And what has it got? 12 different variables with 1-letter variable names. Oh, of course, the entire function is written on 1 line because enters take up a character, spaces between things take up a character. So you've got this like include main. and the main is like another 550 characters. You go, I can't read that. Let's compile it. So you compile it, you run it. What happens? Oh, it draws a Christmas tree, and the Christmas tree spins in circles. And you go, how? I don't know, somebody wrote it. But so the ternary operator is really cool if you use it sparingly. So it can make longer code short, but it can also make readable code unreadable if you overuse it. Okay, so there's our constructor, and we could use a struct instead of a class. The only problem with a struct is if we don't say otherwise, everything's public. So I could use a struct and put like private before the data and put public before the methods. Other than that, struct and class are exactly the same. No memory difference, no speed difference, no nothing. The only difference is if you don't say otherwise. So like up here, I didn't say anything, so those must be private. The other stuff is public. All right, since I've got a constructor, I better have a destructor. My constructor did a new, I better write a destructor. So my destructor deletes the data and sets it to null pointer just for safety. Line 3 is not needed. The only reason to put line 3 there is if someone says, hey, later on, let me make a clear function. Let's make a clear function. Let's take this code and move it into the clear function, and then here I'll just put a call to clear. Code still works because the clear function sets data to a null pointer, which is safe. If I leave a dangling pointer to something that no longer exists, that's unsafe. So that's why I put the data equals null pointer there, is that if I move that code, it's still safe. It takes O of 1 time to delete an array. Now I said here, what if? What if I had a 2D array instead of a 1D array? Well, then we would need to run through the loop n times, deleting every row, and then that would give us a destructor that's O of n time total. Because I had a 2D array, I've got to delete every row inside. Okay, copy constructor. So it says copy constructor, so how do I know, other than the title of the slide, that the top set of code is a copy constructor? What tells you, what identifies it? Yeah?
It doesn't have a return type.
Okay, so with no return type there, that must be some type of constructor. It's a, yep, we got the same type there, must be a copy constructor. So it's a constructor, most likely because we've got no return type, and it's also the same name as the class we're already working on, array, and it's got a parameter of type array. Now the array reference, we said, hey, you should pass things by reference for efficiency. What happens if I get rid of that reference? Yeah. Infinite recursion, because remember, if we pass something by value, how do we pass by value? We make a copy. Who makes the copy? We do. So let's call ourselves. Wait, I need a copy. Call myself. Make a copy, which leads to infinite recursion. The compiler will not accept it. Without the ampersand, the compiler just says no. It's actually a pretty readable compiler error message. It's like, copy constructors are not allowed to use non-reference parameter, something like that. The const is not required. It's just polite. It's saying, I promise not to modify the thing I'm making a copy of. It's not just polite, it's actually in some places it'll be necessary. We'll look at in a couple slides, probably Tuesday, we'll look at places where const is really, really necessary. Okay, so I'm creating a copy. I set my length equal to the other length. I set my data equal to the other guy's data. I run through a for loop and set my data sub I equal to a sub I. Wait a minute, is a sub I, how can I say a sub I when array A is an object? Well, it turns out later on, we're going to overload operator square brackets. So later on, we'll overload operator square brackets. We haven't quite gotten there yet. We could replace this, instead of saying a sub I could say like a dot data sub I. That would work also. So I'm assuming here in line 5 that we're going to implement operator square brackets eventually. So once I have the copy constructor, line 7 line 7 and 8 are just the default constructor. So 7 and 8 use the default constructor to either create an empty one or create one of size 20. Lines 9 and 10 actually both use the copy constructor. One looks like a copy constructor, the other looks like assignment, but the key is that D does not exist yet. Because D is being constructed, we need the copy constructor to copy object B. Now if I say after something's created A equals C, we need operator equals, and if we don't write it, we get a shallow copy, so we better go implement a deep copy version of operator equals. Now, one thing we could do is we could say, hey, let's, instead of writing the copy constructor and writing operator equals and putting a for loop in both of them, how about if I create a copy from function, and then the constructor can call copy from, and operator equals can also call copy from. And this is good. This is not the best way to do it yet. We'll get to the best way Tuesday, I'm guessing. So we're saying, I'm going to write the code once and I'll call it twice. That's good. The downside to this is that in lines 16 and 17, I've got an idiot check. What does the idiot check do? Why is that needed? Yeah. Yeah, like if I've got array A of 10 and, or let's say, yeah, X of 10 and Y of 20, and then I say X equals X instead of X equals Y, what happens? When I say X equals X, I call operator equals. If I don't have the idiot check, I call copy from. Copy from says, delete the existing data. But I'm trying to set X equal to X. I just deleted the only copy of X there is. So it is completely unsafe to do it this way if we don't have the idiot check. The problem with the idiot check, though, is now everybody who uses operator equals pays this constant cost of the idiot check. So everybody that writes good code that says X equals Y has to pay the cost of lines 16 and 17. So we're going to look at, next time, we'll look at a better way to do copying, or should I say the best way to do copying, which is referred to as the copy swap method. The copy swap method is kind of complex. Really, really short code, but it's complex in how it happens. We'll start next time with an example of how this occurs. But read this code, think about what it does before we present it. It'll definitely help.
You said delete this pointer and help us say more responsible. What did you say about if we reverse it?
No, not if you reverse it. If I do this. If I say delete PTR, and then I say PTR is equal to null pointer, and then I happen to sometime later on delete.
That's actually complex. But with that, you get a S and a double delete, so you get to type the rest of the day.
So if I
I don't know how long I make it.
Yeah.
What if I like make it like Tuesday and I'm like terrible?
No, it's hard. So if you have vegetables here, or if you have beer, like your shoes, I just hold it. I love it. Yeah, but it's not. But like, yeah.
So new, when I say new int, it's 4 bytes. But if I say new int square brackets 1, it's an 8 byte size and a 4 byte int. So the square brackets is more versatile, but it takes more memory and takes more time to do and takes more time to be reviewed. So it depends. Whatever new you use, you have to use corresponding to the but which new you use depends on what we want to do. If I want to create a linked list, I'm going to use normal. But if I want to create an array, I can use square brackets. But yes, nothing complicated. So I can move up to call and answer a few more questions.
Just have to say again. Size,